Hello, this is Bob. I'm here to do a mathematical walkthrough of our paper on precision quality control. So previous video gave a conceptual walkthrough. Now we'll just go through the paper step by step and look at the mathematics. So let's just go through here. Here's the introduction, where we talk about what are the goals of the paper, which is basically to look at the trade-off between laboratory risks or costs and patient risk, which is due to unreported errors or errors that leave the laboratory and are reported. So we have results that include some sort of error. And as you know, there's a trade-off between those two things. We can spend a lot of money in the lab to reduce errors, or have a laxer sort of QC policy that is a little more tolerant of errors. So that trade-off is very difficult. So when we look at risk, the fundamental equation here, equation 1, just says that what risk is summing up the loss or the harm, let's just say we'll use cost for loss, of some event, times the probability of that event. So we add up all those instances. So if there's many different things that can happen, we take the cost of one of those, each of those things, times the probability of those things happen. So we get the risk is just defined as the expected loss. And so we can, express losses in terms of costs or various things. So yeah, I think that's the fundamental equation here. And we're going to define what this loss function is and what the probability distribution of these events are. And these events correspond to errors that are not detected and reported and used by physicians. And we talked a bit about loss functions. So the notation we use here is, here's the loss. F sub L stands for loss function associated with some sort of error. And traditionally in clinical chemistry, there's been some models by Parvin, and this model's been used by Westgard and others. It's a threshold model that says that the loss is equal to 1 if the magnitude of the error is greater than the total allowable error, right? And it's 0 otherwise. So this is just sort of a binary model. And this expected number of unacceptable final results is a measure that's used by Westgard and Parvin and others. And it's also part of the mission control software that Biorad uses. I think it's based on Parvin's work, uses this kind of a loss function. So one thing about that kind of a loss function is what we might call a threshold loss function, right? If you're anything below TEA, it incurs no loss or cost. Once you get to TEA, the loss is 1. There's a couple problems with this, and that just look at points 1 and 2. These are separated by a large distance. This error number 2 is very different from error number 1, yet they're given the same loss of 0. In contrast, errors number 2 and error number 3 are as close together as you like, but they have the maximum difference in terms of their cost impact, right? And errors 3 and 4 are kind of the same as errors 1 and 2. They're far apart, yet they incur the same cost or loss. So we can imagine there might be some better kinds of ways of looking at this. We talked about that in the conceptual one, but you can imagine there's all kinds of different tests where different kinds of curves, might be more appropriate. And sort of the general idea is that we would expect any error to have some sort of cost associated with it, and that would it increase as we go along. So yeah, the most common loss function is not necessarily the best one, although it is a very simple one. And you can see that it's convenient for counting, because if we just want to count errors that are greater than TEA, this sort of a loss function works well. But if we really want to look at risk, this is probably not the best loss function, because risk is much more of a continuous function. Whereas if we just want to count the things that are greater than TEA, the threshold model like this is just fine. So One of the things that we need to think about also in a model like this is what happens when we have shifts. Okay, so we imagine that the uh, uh, assay starts out in control, then it undergoes some shift. But the question is, where does it go? The Parvin model and the biorad mission control and so forth make the assumption that it could go anywhere, that any state is equally probable. So these are just, represent various deviations from the target here. And the Parvin model goes, we don't know where it's going to go, so we'll just assume that everything's equally likely. It might be more reasonable to say that, smaller errors are more probable than larger errors. And so when errors happen, they tend to stay close to the target or close to home, and they don't wander very much. Or another possible model is that, when things go wrong, they tend to go wrong in a certain way. So that, maybe there's one sort of thing that breaks on your analyzer, and that causes a shift of 2 standard deviations. So you might see something like this. So I guess the point is just like with loss functions, where you can imagine any kind of loss function that might happen in different contexts. Different assays are different, and they might behave differently with respect to the types of shifts they make. One size doesn't fit all. So when we do this kind of modeling, we need to be really flexible and think about, we need some sort of a model that could accommodate anything. Your assay might look like panel A, panel B, panel C, I don't know what, but we need something that accommodates this very easily. So one other assumption that occurs in the Parvin model and the biorad type model is what I call the shift dynamics. And the assumption they make there is that the system starts out in target, like here in panel A, and that after a time it makes a shift and it never shifts again. That the only place you can have a shift from is being in control. But once you're out of control, you never could have a shift between another out of control state. So if this goes to 2 standard deviations away, it can't shift back to 0, it can't shift to 1, 3, or 2.5, or whatever. That's a pretty unrealistic assumption. So that's one sort of characteristic of the Parvin model that is not really, I think, very realistic. And the problem is that the static approach that's used in those models can't handle more than one transition. And so it's convenient mathematically so that it can be solved. But the system is a dynamic system. It's going to shift and shift and shift over time. And we need a method that can do that. So what we might think about is that the system is in some state, we'll call this S1. And you can make transitions to other states. And we'll just label those here. The probability of going from 1 to 1, staying in the same state is 1/2, and the probability of going from 1 to 2 is 1/2. So all the things that can happen have to add to 1. So as this is going along, there's a 50% chance that it will stay here or it'll move over to S2. Once it goes to S2, it always goes to S3. When it gets to S3, it has a 25% chance of staying in S3 or a 75% chance of going back to 1. So you can see that in this kind of system, it's a dynamic system that evolves over time. Some of the time it spends in state 1, some of the time it spends in state 2, but it just kind of goes around and around. And we can summarize the probabilities in this transition matrix here. So here's state 1, and we can see there's a 50% probability of going to state 1. Once we're in state 1, there's a 50% probability of going to state 1 or a 50% probability of state 2. And so these are convenient ways of representing a dynamic system mathematically. So this is a state transition diagram, and this is a transition matrix. Okay, so we have this state transition diagram, And you can remember from the conceptual video, we need to specify all the parts of that diagram. And one of them is the states. And so equation 3 here in the paper just as a way of listing those. So we describe this in terms of M and D. Okay, so M is the range. So if M was 5, we would be looking at states that go between -5 standard deviations and +5 deviations in steps of D. So it's just a way of listing all these states. So, you know, if I had 60 states, I'd have 60 bubbles here. And, you know, say like M was 3 and D was 0.1, I'd end up with 60 states that I'd need to put on a state transition diagram. So this is just a listing of all the states that can happen. And the means that we can see are, we call them mu sub n, is an element of this set of states. Okay, so we call this set delta, and delta is a function of m and d, and this is just set notation of listing all the elements of that set. So we also have a detected state. So there's a bunch of states that correspond to shifts, but when the system is detected, it moves to a detected state and then goes back. Okay, so then all the allowable states is given by S. We give big S for the set that contains every state, and that's equal to delta, which is the set of all the shifts that can happen up here, plus the detected state. Okay, so it's just more than one. So the total number of states in S, it's the cardinality of it. If we were to, the number is just 2m divided by d plus 2. And for every state, we just call it S sub I. For state I is S sub I. Okay. We'll designate S sub 0 as the in control state, where it's on target and there hasn't been any shift, and S sub D is the detected state. I think we can skip this. This is just talking about, we can designate subsets of the state space as in control and out of control. And usually, for most purposes, we'll think of an in control state is when there's no shift at all and the system is on target. But you could imagine circumstances where you go, you know, there's small shifts of like a standard deviation of 0.1 or something that I don't really care about. And I would consider that in control as well. Because we want to think of circumstances where it's a waste of time to troubleshoot and recalibrate and get the system back online. And you might consider a broadened definition of of in control. And this notation here in lines 207 to 213 just does that. Okay, so we're going to think about transition behavior, and what we're going to do is describe these transitions between states using a transition matrix, just like we did over here. Okay. And the transition matrix has to include all the states that we talked about. So the states went from -m to m in steps of D. So that's given here. So this matrix can be quite large. And in fact, when we solve our sample problems, it's, I think, 120 by 120. And it also has the detected state over here. So this transition matrix just describes what happens to the assay if we let it run by itself without any influence from the quality monitoring system. Okay, there's no such thing as a flag that looks for a control rule violation, right? So the system is just running under its own influence by itself. And each of these elements, remember, describes the probability going from this state to this state. So all the H's are probabilities of staying in the same state, okay, of staying where you are, of not, deviating from home. And all of the G's describe the probability of going away from home. And if you do leave home, what's the probability of going here, or going here, or going here, or going here? So this is very general. Unlike the Parvin type model, where we assume that you just can go to one state and stay there till it's detected, here we assume the assay can undergo a random walk where it just moves around from state to state. And by giving different values to this, we can really prescribe how that happens. For example, if the H's are big, it means that the system is very stable and tends to stay in the same state. And it'll stay here for a long, long time. Let's say H was 0.99 here. Well, given that it's in this state, there's a 99% chance that it'll stay there. Okay. And then we can give different values here for the leftover 1% of what happens if it decides to leave here, and so on and so forth. So this is a very, very flexible way of modeling. And typically why we use this notation here of using all the H's on the diagonal, we might want to just specify that the stability of the system, its tendency to stay in the same state, is some number. And that way we could make all these H's the same, say 99% if we had a stable system, or we could make it 0.9 if we thought that the system left its current state 10% of the time. And similarly, we can describe where it goes when it leaves with these G's. So that gets back up to here. Do we think it's a uniform distribution that if it leaves this state, it goes anywhere else with equal probability? Does it tend to stay close to home? Does it tend to center its someplace, and so forth? So we would describe that sort of behavior with the G's. Okay. So this T sub A means it's the transition matrix for the assay alone, without any influence of the quality control system. Okay, so it's sort of what it's doing is showing the intrinsic behavior of the assay. Okay, sort of and it captures the stability of the assay. Okay, so down here we start talking about the QC monitoring policy. And what we're going to do is talk about how the QC monitoring policy affects the natural behavior of the assay. So that will be layered on top. And we're just going to, for the purposes here, we could use any monitoring policy we want. This model we're developing is completely flexible, but I think for the problem we'll look at, we'll just assume a 2 standard deviation control limits. Okay? And that'll make things pretty simple. So the thing about a QC monitoring policy is we'll end up with some sort of power curve, right? We talked about that in the conceptual model, and we call that a probability of detection of some state S given a QC monitoring policy pi. So pi can be anything in our model. It can be Westgard rules, it can be Q sum, it can be exponentially weighted moving averages with any parameter you want. It can be anything you can dream up. So our model is completely flexible with respect to this. So all we need to do is create a power curve for that, and the model will accept it. And there's no problem, no limitations at all. Then the next thing is when we add in this behavior of the quality control system, what happens? Well, now let's say we're in a state, we can stay in the same place, but it depends on the probability of detection, right? We can detect, say, if we're in a state that's away from 0, that there's been a shift, in which case we go over here to the detected state. And this says, here's the probability of detection that I'm in this state over here. So that's the probability that I'll end up here, given that I'm here. Otherwise, if I'm not detected, I can make a transition to any other state based on the natural evolution of the behavior of the intrinsic properties of the assay, like we talked about. It just it meanders around and around. So this is just a matrix that combines both the effects, the intrinsic behavior of the assay with the extrinsic behavior of the quality control system, detecting things and altering it. So whenever we have a detection, we have to start over. We go back to state 0, and the whole system goes over again. But this describes the probability of every transition between a state. And then just very formally, what we want to show, and the whole point of this is not to have a bunch of math, but it's just to say that we can describe the behavior of the system, and that's the combined behavior of the intrinsic behavior of the assay plus the overlying influence of the quality control system as a function. We can do that very formally, and that just shows how to do this. It's kind of messy, but I think it's sort of important to recognize that, yes, the behavior of the system, the transitions that happen, are determined by the behavior of the assay alone, plus the overlying influence of the quality control system, which is given in these matrices D and C. So you can see that D depends only on the probabilities of detection, right, which is just from the power curve, and C also just depends on probabilities of detection. So these matrices are comprised of data that come from properties of the QC system, where T sub A is comprised of data that just comes from the intrinsic behavior of the assay alone. So there's two different things combined to give the overall behavior of the system. So we can figure all that out if we know these matrices. So what we're going to look for here, and what is very different about the precision QC model and models that have preceded it, is this is a dynamic model. We're looking at the long run behavior of the system over time and looking at how much of the time does it spend in various error states before it's detected. Okay. So what we do here is we have this transition matrix for the system, and we have a vector over here, PSS, which stands for steady state. And so what we're looking for in the steady state is when PSS is multiplied by TSS, you land up in the same state, right? That's the whole definition of a steady state, in that you don't move at all. So what we want to do is find this vector. So PSS is the long range probability distribution of what will happen if we apply this kind of quality control system on a particular assay with its own intrinsic behavior, run it a gazillion times. What will be the probability of being in any individual state in the long run? And that's what's given here. So this vector PSS has all the states in it, but it also has the detected state in it. The detected state is just sort of a artifact. We put it in there for convenience for modeling, but the system doesn't spend any time in the detected state. It just flows through it instantly and goes back to being recalibrated. So when we calculate what the probability of being in some error state is, we need to take out the detected state and just correct for that. So that's what's going on here. Okay. So now we talk about loss functions, okay? And those can be anything in our model. It's absolutely completely flexible. You can designate it any way you want. Okay, there's no limitations whatsoever. So in a loss matrix says, what is the loss that happens when I make a transition from one state to another? So if I go back here to, where are we? This diagram, there's some probabilities of going from state to state to state, but we're also going to say that when we go from state 1 to state 2, there's some cost involved. It could be 0, it could be something positive, but basically what we're going to do is add up these costs every time we make a transition between one of these states. Okay? So what we can see from our assay is the assay is going to move from state to state. Some of those states are associated with large errors, and we'll assign big costs to those. Some of the states are assigned with correspond to small errors or no error, We won't incur any cost. We're in those states. So basically, we're just going to add all of those up. And so this is just the giving the loss function in the sample loss function of each element of the matrix. So if I make a transition from one place to another, so B is the batch size. And so the losses that I incur, so let's imagine that I have a batch size of 1,000 and I report out a batch with some sort of error. Well, it'll be the batch size, say 1,000 times the cost of having that error. So that's why you see these B's in here. Okay. And this just says, here's the loss of having reporting a shift or an undetected error that if I've made a transition from state I to state J. Now we also have a loss function for false positives, right? So same sort of thing here.